Okay, recording has started, so good morning everybody and welcome back to Math 115. I say everybody, we're down to 6 students. That's okay though, if you guys are watching remotely, that's perfectly fine. For the people who are here, how's everything? Doing okay? Close to a month left. Man, is it that far already? Yeah, I guess you're right. I think about it, one of my finals is going to be due on like April 29th, which is exactly 1 month away. Yeah, kind of crazy. Only a month left. Morgan, doing pretty good. Excellent. Okay. Well, let's see. Last time, or last week, last couple of weeks, we've been talking about these trig functions. So what we're going to do this week, aside from the fact that tomorrow is a wellness day, so we don't have any class tomorrow, is we're going to continue talking about trig, and we're going to dig a little bit deeper into this trig stuff and do some more complicated examples. But first and foremost, I don't want anybody to forget that the third exam is going to be on April 8th. Okay, so it'll be the usual protocol. I'll post a practice exam towards the end of this week, I think, and then I'll post a practice guide solution thing to the practice exam. And then next week on Thursday will be your exam. So at 9 a.m. or at like 8 a.m. I'll put it up on the blackboard. And then you'll have until 9 p.m. that day to complete the exam. And email it, or not email it, but submit it onto Blackboard as a PDF. Okay? And as usual, also we'll have one review day next week as well. So it might be good to start accumulating questions now to ask during the review day on Wednesday or during office hours this week or next week, so that you're all prepared for that exam. Okay? So last week we talked about inverse trig, and this week we're going to talk more about identities and formulas involving trig. Okay, there's a ton of formulas which I'm going to have to throw at you this week. So hopefully that's not too overwhelming. But the good news is, on the exam, it's open book, open notes, so you can find all of these formulas in the book or in the notes for this class. So if you want to do that, that's perfectly fine, and you don't necessarily have to memorize all these formulas like I did when I was a pre-calculus student, which was terrible. And I don't think it was particularly useful either, because I don't remember any of them now. I just looked them up online. So that's how I'm going to present them to you guys. And don't forget, we also have no class on Tuesday, March 30th. That's tomorrow. It's a wellness day, so you need to go and try to improve your wellness as best you can. Okay, so before we get started on the new stuff, let me go back and talk about what we learned last time. So what did we learn last time? Last time we had already kind of covered inverse sine, so we reviewed how to do inverse sine, and then we learned how to do inverse cosine and inverse tangent. Okay, and there are other inverse functions for the secant function, cosecant, and cotangent, or whatever. But I'm choosing not to discuss them because, to be honest, it's fairly rare for them to pop up. I think knowing of their existence is enough. Okay, so just to remind everyone about what is the game that we're playing with this inverse stuff. Okay, what we want to say is, okay, before trigonometry for us was, okay, given an angle, theta, can you tell me what are the properties of the point on the unit circle which correspond to that angle theta? And now, rather, instead, we're going to be given a point on the unit circle, or even just one coordinate of the point on the unit circle, like the y-coordinate maybe. No, in this case it was the x-coordinate. And then they say, okay, given this x-coordinate and the fact that theta should be between 0 and pi, what's the unique angle theta, which is going to be able to be put here such that the angle points at that particular x value. Okay, so that was the reverse, or rather the inverse trig game. Okay, and in order to make our answer unique, we did have to sort of specify whether we were on the top half of the unit circle or whether sometimes we're on the right half of the unit circle. Okay, so the way it worked was for sine, we're always talking about the right half. Right half. And for cosine, we're always talking about the top half. Okay, so that was about how we do inverse trig and also tangent, sine and tangent. Oops, that wasn't what I wanted. Sine and tangent were both right half. Okay. So we talked about inverse tangent. Inverse tangent was a little bit trickier than all of the other inverse functions. The reason being that this value which we wind up getting given, okay, the value which we get given is actually going to be the height of a point on the tangent function, which is a little bit harder to understand on the unit circle because it actually manifests as this kind of distance from this point to the x-axis if we take this kind of tangential route. And that's a little bit harder to understand, I think. So the way we understood it was, well, we don't know what the y value or the x value is of the point on the unit circle, but I know what the ratio is between them. Okay? I know what the ratio is between them. And if the ratio between these two side lengths looks like the ratio between side lengths of a special right triangle, then I'm sort of in good shape. Okay? I'm in good shape. And I can sort of figure out what this angle should be using a more geometric interpretation of what's happening here. Okay, so sadly, we kind of lose that nice Pythagorean theorem that was really helping us to do these inverse problems before. And now we have to rely a bit more on our intuition. Okay. So here is a table that I wanted to share with you all. Okay, so this is in the notes, so if you want to go back to the notes at some point during your exam or something, then that's fine, you can check this out. Okay, so these are the domain and range of all of these untransformed inverse trigonometric functions. Okay, so what do we see? We see that the domain of the sine and cosine, I'm sorry, the domain of the cosine inverse and sine inverse functions, okay, are that the x value should be between -1 and 1. Why should that be true? Well, that should be true because if we take an angle theta and we plug it into the sine function, well, it's going to give us a point on the unit circle, or the y-coordinate of a point on the unit circle. And the largest possible y-coordinate would be up here at +1, and the lowest possible y-coordinate would be down here at -1. So if we want to take a point on the unit circle, this domain of the inverse function should describe the, like, all possible y values of points on the unit circle for sine inverse. And for cosine inverse, it should describe all possible x values of a point on the unit circle. Okay, and then the range is going to be basically our limited perspective of where we're going to search for an angle which has that y value. Okay, when we're working with sine, we're working with -π/2 to π/2. So -π/2 is straight down and π/2 is straight up. So we're only going to look on the right half of the circle for an angle theta, or an angle, in our case, an angle y, such that if we plugged it into cosine or sine, we would get x. Okay, and we're going to check only on the right half of the circle for sine theta, because otherwise we would get more than one answer, and we only want one answer. And then for cosine, we're going to check between 0 and pi. So for cosine, it's just the top half of the circle that we look at. Okay, and it makes sense that these cover all of our possible y values. If we look at the sine one, all of the possible y values are accounted for in that green portion of the circle. And on the cosine one, all of the possible x values of our unit circle are accounted for in this green region. So that's kind of the logic behind that. Okay, and then if we want to look at what is the domain and range of the tangent inverse function, well, again, our range is going to be just the right half of the unit circle, except we are going to exclude those points π/2 and -π/2, because those produce those tangent is not defined for those values. So there's no value which we can plug into tangent inverse and get those points. Okay, and the domain will just be any number which is between -infinity and infinity, because tangent can produce a point of any height. Okay, the graph of tangent can produce a point of any height. So the domain is going to be, well, if we just consider what are the possible heights of those functions, of that function, well, it's -infinity to infinity. Okay, and so on and so forth. So these ones down here, they exist, and these are their domains, and if you want to memorize them, then you can. I don't think that they're particularly useful, especially not for the purposes of our class, or probably any of the other math classes that you would take here at U of SC, unless you're a math major, in which case come talk to me and we'll talk about those functions. Okay. So before we started on the new stuff, I wanted to do a couple more examples of this inverse stuff together to give you guys a little bit more structure on how this is done. Okay, so I'm going to work through these two examples. Maybe we'll even do 3 examples. And I want you guys to follow along on your notebook and see if you guys can kind of complete this as I go. So if you can work a little bit ahead of me, then I think you'll be in good shape for the exam. Okay, so the first question is to find out, okay, what is sine inverse of -1/2? Okay, so what I'm going to do is I'm going to immediately draw a unit circle. And I'm going to immediately not care whatsoever about the left half of the unit circle. I'm only caring about the right half of the unit circle, because I know that sine inverse should produce a value of theta which lies between -π/2 and π/2. So forget about the left half. Okay, and now what do I want to do? The input of the sine inverse function should be the y value of the point on the unit circle. So what do? I look for a point on the unit circle, which is on the right half of the unit circle, and its y value is -1/2. So that would probably be somewhere down here. Well, I know that all the way down is 1, so 1/2 should be basically halfway down the unit circle. So maybe our theta looks something like this. Okay, so in this case, theta is going to be a negative angle. Okay, you can also tell for sure, all right, that our angle should be in quadrant 4, because sine of our angle gives us a negative result. And we know that all trigonometric functions are positive in quadrant 1, and you see only cosine is positive in quadrant 4. So we know we should definitely be in quadrant 4. Okay, and now what do? I'm going to fill in a little bit of the information of this point. I know that this is the point something, comma, -1/2. And as always, I'm going to draw a gosh darn triangle. So here's our triangle. We know this is a right angle. I know because the y value of this point is -1/2, I know that the length of this side here is 1/2. I also know the length of another side on this unit circle. What's the other length of the other side that I know of this triangle, which is inside my unit circle? What is it? That's right, the radius. Okay, the point which goes from the center of the circle all the way to the outside of the circle is a radius. So I should exploit the fact that I'm working on a unit circle here. I know the radius of the unit circle. It has radius 1. So this length here is 1. Okay, so if I have a triangle which looks like this, and one side length is 1/2, and one side length is 1, what is the other side length? What should the other side length be? Less confident. Okay, well, I get the side length of the hypotenuse by taking this side length and multiplying by 2. So that maybe reminds us of a special right triangle. This is the relationship between the sides of a triangle, which is a 30, 60, 90 triangle. So this 1/2 will be across from the 30, the 1 will be across from the 90, so what should be across from the 60? It should be whatever is across from the 30, which is in our case 1/2, times the square root of 3. So this side should be square root of 3 over 2. I think Abdul Rahman got it there. Okay, so that's just a special right triangle. But okay, say for the moment that you forgot that this is a special right triangle, and you only had just that this is what we have. You can use the Pythagorean theorem to figure out what the other side length is. If this side length is b, then you say, okay, we take 1/2 squared plus b squared is equal to 1 squared, and therefore we get b squared is equal to 1 minus 1/4, which is 3/4. And then you would just take the square root of both sides, and you'd get b should be equal to the square root of 3 over the square root of 4, which is equal to the square root of 3 over 2. Okay, so no problem. If you forget that this is a special right triangle, don't fret. Just use the one theorem that you've probably memorized and know how to use pretty down pat by now. Just use the Pythagorean theorem. Okay, anytime we have a right triangle, we can use that theorem as much as we want. Okay, so this side length here is square root 3 over 2. Okay, and hopefully at this point, you recognize that the relationship between these three sides is satisfying a special right triangle, because we are going to need to know the angles inside this triangle in order to find out what the angle theta is. So I know that there's three angles in here. One of them's 30, one of them's 60, one of them's 90. And I know that across from the smallest angle should be the smallest side length. Okay, since 1/2 is across from the smallest angle here, this is going to be our 30-degree, and then the one that's has the square root 3 is going to be, well, I shouldn't say the one that has the square root 3. I should say the side length, which is medium, is going to be across from the medium angle, which in our case is 60. And then the longest side length, which is 1, is going to be across from the 90. Okay, so I have a 30, 60, 90 triangle. So what is this telling me? This is telling me exactly what theta is. I have theta is equal to 30 degrees, or in this radians, you could write pi over negative pi over 6 radians. All right, so that's how we do this one. Any questions about this inverse trig problem? Let me poll you for your confidence. Okay, how confident do you feel like you are with this material? If I had given you this problem today on a pop quiz, on a scale of 1 to 10, how well do you think you would have done on the quiz? Nine with notes, 7 without. Okay. All right, well, here's what I'll say. If you're feeling a little bit less good about this, please come to office hours either today or on Wednesday, and we'll talk more about inverse trig, and I'll show you a ton of different examples, and we can go through a lot more. Okay. For now, I'll do just one more example. We'll try this one, arc cosine of pi over 2. Okay, so I know I want to find the angle, which, oh, this is dumb. Okay, arc cosine of pi over 2. So this input here is a x value, hopefully, of a point on the unit circle. And the output of this function should be an angle theta. So I'm already a little bit confused because the input kind of looks like an angle. Okay. In fact, here's what we can say. We learned already that the domain of the cosine inverse function is -1 to 1. But pi over 2 is equal to like 3.14151926 ... all divided by 2 is larger than 1. So this function for this input is undefined. Okay, silly question. But what is it really asking? It's saying, essentially, the following. It's saying if I have a unit circle here, find me the angle theta, which is between 0 and pi, such that the point on the unit circle has an x value of negative pi over 2. But the issue is that negative pi over 2 is like way over here. So the question doesn't make sense because there's no points on the unit circle who have an x, oh, sorry, not negative pi over 2. Should have been pi over 2. Which is like over here. The question doesn't make sense because there's no points on the unit circle whose x value is pi over 2. Okay, so the input was not in our domain, so the question doesn't make sense. All right. Same deal with this one, also undefined. Okay, let's do this last one here. Arctangent of -1. Okay, so what do we want? We want the following. This is telling us that the ratio between y and x is -1. So y over x is equal to -1. And therefore, y is equal to -x. This is what we're learning. Y is equal to -x. Okay, we know we should be working on the right half of the unit circle. So x should be a positive number. Okay, and then y is going to be a negative number, which means we're going to be really in quadrant 4 here. Okay, so what am I going to do? Well, I'm going to draw some angle which goes into this region. And again, this is not really going to be to scale. But I'm going to draw it, and I know that this is the point x, comma y. But I actually know what y is. Y is just -x. So this is really the point x, comma, -x. So if I were to draw in, I'll use my dotted line as usual. If I were to draw in my triangle here, then what properties does our triangle have? Our triangle has one side length, which is 1, one side length, which is x, and another side length, which is the same as the first side length. Someone tell me what kind of triangle has the property that two of its side lengths are equal? What kind of triangle has this property? That's right, 45, 45, 90 triangle. Salmon of Durman, got it. So we know that these angles inside here are 45. Just by virtue of that. Okay, there's only one type of triangle who's got a right angle on the inside and two of the side lengths are the same. It's a 45, 45, 90 every single time. Okay, so what is that telling us? Well, it's telling us that our angle theta here, which produces a value of -1 for tangent, is the value theta which is equal to either 45 degrees or -π/4. Okay, so that's how I'd find my answer. Okay, any questions about how I did this arctangent problem? Yeah, sorry. It should have been negative 45 degrees. So negative pi over 4, you're right. Okay, if no other questions, then we'll move on and talk about new stuff. Okay, so here's what we're going to learn how to do now. So 5.1, honestly, is a little bit of a confusing section because it sort of feels like something we've already talked about. And this stuff which is in this white box may seem sort of familiar already. And that's because we already had a section where I talked about all of these identities. But what we're going to talk about next, okay, is how to sort of use what we know about these trigonometric identities to either verify other ones which aren't as simple, or derive new ones, or check whether certain relationships are true about these trigonometric functions. Okay, so this here, what is written here is not really the content of the section 5.1, but rather this is the background information which will be sort of indispensable for what our goal is for this section. Okay, so let me remind us of what these identities all are. Well, cosecant of x is 1 over sine of x. That's sort of the definition. Okay, all these other ones, same deal. Okay, we can define, or we can look at any of these trigonometric functions as 1 over their reciprocal. Okay, and then the quotient identities are, yeah, okay, tangent of x is equal to sine x over cosine x. Cotangent of x is equal to cosine x over sine x. That shouldn't be too surprising. And then the main ones that we learned were these Pythagorean identities. Okay, so sine squared x plus cosine squared x is equal to 1. That's the very most important one that we have. Okay, and then if we take that one that's circled in pink and we divide everything by sine squared of x, then we get the second one, which is 1 plus tan squared of x is equal to secant squared of x. Sorry, if we divide everything by cosine of x, cosine squared of x, then we get the second one. So this is equation 1, and this is if we take equation 1 and we divide by cosine squared of x. And then this is equation 1 if we divide by sine squared of x. Okay, so those are the Pythagorean identities. And then we had a couple even and odd identities. Okay, so in particular, we have cosecant. Oh, that does not show up well, does it? We had that cosecant. No, what am I talking about? Sorry. We had secant and cosine are our even functions. And then we said that everything else is odd. Okay? Everything else is odd. Okay, so what are we going to do? We're going to take all of these identities and we're going to do like this meme dude is doing. We're going to take one and another one, and then we're going to combine them and make something new. Okay, or something along these nature, or along these lines. Okay, so this is where we're going with this stuff. Okay, so don't forget, you can always come back to these notes on the exam and check these identities here. Okay, if you have a problem and you're trying to figure out how to rewrite something, try out these identities and see if rewriting them in that way helps you. Okay, so here's an example. We want to verify whether the following equation is true, and the left-hand side just looks kind of atrocious, and the right-hand side doesn't really look that much better. But here's what we're going to do. We're going to try to take this equation on the left-hand side Okay, and we're going to rewrite it a little bit and see if we can rewrite this left-hand side a few times and eventually end up on the right-hand side. Okay, so here's what I'm going to do. Let's check this equation and see if we see anything which looks like this in our sort of bank of identities. Okay. The reason I'm going to check this is this looks vaguely Pythagorean Theorem-esque. It looks like the square of something minus the square of something else. Okay, this kind of reminds me of Pythagorean Theorem. So let's check. Let's see if there's anything involving cosecant squared and the number 1 in our table here. Well, if I look at my Pythagorean Theorem identities, I see one of them does indeed involve cosecant squared and the number 1. Okay, so what I'm going to try to do is rewrite that equation down here. So let's remember, this is just a side note. I know that, what was the identity? 1 plus cotangent squared of x is equal to cosecant squared x. So what I can recognize here is that this numerator of this quotient here, the numerator looks kind of like if we rearrange this equation a little bit. So if we move -1 over to the other side, then we would get the equation that cotangent squared x is equal to cosecant squared x minus 1. And now I can see something. This right-hand side here, cosecant squared x minus 1, is exactly our numerator of our fraction here. So I'm going to replace the numerator by something which is equivalent. So I take the following. I say cosecant squared x minus 1 over cotangent of x. Well, I know that this is just equal to cotangent squared x divided by cotangent x. And if I have, x squared divided by x, I get just x, right? So if I have cotangent squared and I divide by cotangent, I just get cotangent x. So we've verified the identity. We started on the left-hand side with cosecant squared x minus 1 over cotangent x, something which looks kind of a lot different, okay, than the right-hand side of our equation here. Okay, and then we wound up through the use of our identities and basic cancellation and stuff. We wound up on the right-hand side, which is where we wanted to be. So this is how we verify an identity like this. Okay, and there's a lot of different ways that you could approach this. For example, what I could have done instead is the following. I could have started with cosecant squared x minus 1 over cotangent of x. Cotangent x, which is equal to cotangent x. I could have checked, well, is this true? By just multiply both sides by cotangent x. And then we cancel the denominator on the left-hand side, and we get cosecant squared x is equal to cotangent squared x. Sorry, one of them should have had a minus 1. Cosecant squared x minus 1 is equal to cotangent squared x, and then I'd add 1 to the other side. And this is exactly one of our Pythagorean identities. Okay, so one of those two ways is good for verifying this identity. So what we want to do with these verification problems is as follows. We want to start on the more complicated side and see if we can apply basic algebra and our library of identities to rewrite it in a clever way such that when all the dust settles and everything is canceled out and rewritten as needed, we wind up with the simpler expression. Okay, this is how we do this verification stuff. Okay, so let me show you another one here. Oh yeah, sometimes they're going to ask us to verify whether something, is an identity or not. Okay, so sometimes they tell us to show that something's not an identity. Okay, and what you want to do here is take this equation and rewrite it in such a way that it becomes obvious, okay, that the right-hand side is not equal to the left-hand side. For example, if we could rewrite this after some work as like the equation 1 equals 0, and we know this one's not true, and we know that the top is equivalent, then we know that the top is not true either. Okay, so that's where we want to go. We want to kind of rewrite this equation in a way that it looks very clearly impossible to be true. Okay, so can someone give me a really quick and easy argument why we might expect sine of x minus cosine of x quantity squared to not be equal to just sine squared x minus cosine squared x? Why should these things not be equal to one another? Maybe someone can give me a really slick argument here without even really having to do any rewriting. Not quite, Heidi. I'll explain that in a minute. That's a good thought, though. We should explore whether that's true or not. Maybe I can ask it in this way. If I have one number plus another number and I square it, do I just distribute the square and get a squared plus b squared? That's right. We only distribute with multiplication or division. Okay, so when we take a power here, in particular, I mean, what do I do when I have two things added together and I square? There's one word that I'm looking for here, which is what we do every time we have a binomial like this and we square it. That's right, FOIL. That's what I'm looking for. We would have to FOIL to expand this. This is a plus b squared. If we have 2 written like this, we got a FOIL. We would get a squared plus 2ab plus b squared. So the 2ab here, okay, we get this extra term. Okay, so if we have a sum of 2 things and we square it, we're not just going to distribute the square onto each term. Okay, we're going to wind up with a middle term. Okay, so let me really quickly address another comment that came in, which was, well, should this, if I do sine of x and I square it, is this equal to sine squared of x squared? And the answer is not quite. The reason is if I have f of x and I square it, I get f squared of x. Okay? The reason is that this f of x here is its own term. Okay? So the input here is attached to the function. Okay? So these two things notationally mean the same thing. Okay? If I write f of x and I put it in parentheses and square it, that means the same thing as when I write f squared of x. Okay, so for this reason, we do not square the input of our function, okay? And it can be a little bit confusing when we write sine of x because I kind of leave off these parentheses here, but we need to remember that this sine of x is a function and x is being plugged into it. So if I square it, I get sine squared of x. Okay, so we don't write the parentheses every time. This is just how the book does it, and this is how it's done in practice. A lot of the time, if you have a sine function like this, you just leave off those parentheses just because it takes a really long time when you're writing a lot of trigonometric functions to write all the parentheses out. Okay, so this equality is true. Sine of x squared, we get sine squared of x. Or sine squared of x like this is also fine. Okay, so that's addressing one comment that came in the chat. Okay, so what should we do? We should try to rearrange this in a way that we get something which is obviously untrue. So I'm going to just FOIL out this first term. I would get sine squared x minus 2 sine x cosine x plus cosine squared x. And I want to check, well, that this is not equal to sine squared x minus cosine squared x. Okay. So let's see here. I'm going to maybe subtract over sine squared x and subtract over cosine squared x as well. Subtract sine squared x. These ones cancel. Subtract cosine squared x. I get negative 2 sine x times cosine x is equal to negative 2 cosine squared x. Well, I can cancel the negative 2's, and I can cancel one of the cosines. And I have the equation, ultimately, sine x equals cosine x. Or not equals. And this is true. Sine x is not equal to cosine x. In fact, it's not equal to cosine x for most values of x. But all we need to do is show that there's at least one value of x for which these are not true. So here's sine x, and here's cosine x. So just pick something like, I don't know, x equals pi over 2. For x equals pi over 2, sine of pi over 2 equals 1 is not equal to 0, which is equal to cosine of pi over 2. Okay, so that's how we can show that these things are not equal. We just rearrange all of this stuff until we arrive at something which is so obviously in our face untrue that we can just kind of conclude that the original thing, which we arrived at through just basic algebraic manipulation, should also not be true. Okay, so we can use this same kind of rearrangement argument. Okay, I'm going to close here for today. So if you have any questions about what we just talked about, or any questions about trig or inverse trig or anything that we've covered in this class so far, please hang around. Office hours start now and go until 10:30, so I'll open it up to other students for questions. Otherwise, everybody have a good day and see you on Wednesday. No class tomorrow. Thanks, Heidi, you too. Jake, you have any questions? I don't really understand completely about theta. Okay. So let me add a page in here. So regarding this symbol theta, you mean don't really understand what it represents, or why we use the Greek letter? Okay, so theta is just a letter we use, okay? So you know how in math sometimes we use X or Y or A or B, and what we mean when we write one of these letters is it's a placeholder for some number, right? We call that a variable. Okay, it's a letter which is a placeholder for a number. And theta is also a variable. Okay, so theta is just a placeholder for a number. Okay, and it's tradition in mathematics to use the variable theta whenever we're talking about an angle. Okay, so sometimes we use theta when we're talking about an angle. Okay, so for example, if theta is equal to 30 degrees, then we could draw it in the following way. So here's a unit circle. And maybe I can ask you if we've got quadrant 1, quadrant 2, quadrant 3, and quadrant 4, in which quadrant do we think that 30 degrees is going to point? Yep, quadrant 1. And let me draw 3 lines in here, and you tell me which one is the most plausible to be theta. Red, green, or blue? Blue, that's right. Okay, so this angle here is theta equals 30 degrees. Okay, if you want to know how to figure that out, well, all you have to do is say, well, I know that 30 is exactly 1/3. 30 degrees is exactly 1/3 of a 90-degree angle. And I know a 90-degree angle looks like a perfect corner, right? 90-degree angle looks like this. So if I were to just cut this into thirds, then I just take exactly 1/3 of it, and that's going to be 30 degrees, right? So I think you got a good intuition for that. Okay, so that's how we measure things using degrees. So theta is just a letter that we use, like x or y or z or whatever, to describe a number, but typically theta is traditionally the letter that we use to represent a number which is a measurement of an angle somehow. Does that make sense? It does make sense. Okay, cool. So was it just that you needed a little clarification on what the letter was talking about, or you want to talk more about some of this trig stuff? Okay, how do you find sine and cosine? Sure. So that was something that we defined at some point, which was the following. So let me take another step back and say, do you have a good grasp on what the unit circle is? You think so? Okay, so could you tell me what is the equation of the unit circle? Two pi r is an equation for the circumference of a unit circle. Actually, 2 pi r is the equation for the circumference of a circle with radius r. But I'm looking for an equation for the unit circle which involves x and y. Not sure. Okay. So back during like one of the previous lectures towards the beginning of class, we had the following proposal. We said if we have a circle whose center is the point h comma k, and the radius of that circle is r, then we said that the equation of this circle with center hk and radius r is x minus h squared plus y minus k squared is equal to r squared. Does this look familiar at all? Okay. So this is what the equation of a circle is, and let me just explain what it means. It means that if we take any point which is on the circle, and we take the coordinates, and we plug them in for the x coordinate and the y coordinate here, then this equation is going to be true. Okay? So the special thing about the unit circle is the center of the unit circle is 0, 0. And the radius of the unit circle is 1. So in our equation, we would get x minus 0 squared plus y minus 0 squared is equal to the radius squared, where the radius is 1, so that's 1 squared. So if we simplify this, we get the equation x squared plus y squared is equal to 1. Okay, so this is the equation of the unit circle. So for a given point on the unit circle, if we have some point here, x comma y, or it could be somewhere else, it could be over here, x comma y, wherever, anywhere on the unit circle. If we take those values of what the x value is, and we take the y value, and we plug them into this equation, it should be true. Okay, that's what it means for this to be an equation of a circle. Okay, are we up to speed so far? Or still confused about some of that stuff? Yeah, let me get to radians in a minute though, because first I need to tell you what sine and cosine actually mean. So if we have an angle theta here, okay, well, the whole point of trigonometry is for any angle theta which you give me, I can put it inside of the unit circle. So for example, this angle 30, I can put it inside of the unit circle where one side of my angle points straight out to the right and the other side points somewhere else. And the crux of all of trigonometry is that no matter what angle you choose, there will be a point somewhere on the unit circle. Such that the angle which you gave me points directly at that point on the unit circle. Okay? So, for any theta that you give me, I can put this in direct correspondence with a point x comma y on the unit circle. Okay, where depending on the angle theta you give me, I will know exactly what is x and what is y. Okay? So sometimes the way we write this is that p of theta is equal to the point x comma y. In other words, the left-hand side says the point on the unit circle which corresponds to a given angle theta has coordinates x comma y. That's what this equation means. Okay? So in this case, p of 30 degrees is equal to the x and y coordinates which go with 30 degrees. Okay? So let's see what those x and y coordinates actually are. If I drop a line here, then I have a triangle, and the side length here is 1. So if I were to remove this from the unit circle, what would it look like? Oh, come on. It would look like this. This side length is 1. This angle is 30 degrees. This angle is 90 degrees. Can you tell me what are the lengths of these two sides? What is 60? The length of this side is 60 units? I think you're on the right track. 60, the number 60 does fit in to this somehow. But how does it fit in? I'm interested in knowing what are the side lengths of this triangle. That's right. The 60 is going to go in here. It's going to be the angle here. 60 degrees is on the inside. Okay, so I have a triangle. One angle is 30, one angle is 60, and one angle is 90. So how do I find what are the side lengths of these two side lengths? If I know the side length of the hypotenuse, is there a way I can figure out what the other two side lengths are using the facts that I know about 30, 60, 90 triangles? No, not the unit circle. We're going to return to the unit circle in a minute. But for now, we're just trying to say something about this triangle. Is there a relationship between the lengths of the sides of a 30, 60, 90 triangle? Okay, so we agree there's a relationship. Okay, so let me ask you this. What should be the relationship between the length of the side, which is across from the 30-degree angle, and the length of the side, which is across from the 90-degree angle? Multiplication is involved. Okay, let's maybe give it a name. Let's say that this side length here is y. If I know that the side length across from the 30 is y, and I didn't know what the side length on the hypotenuse was, do you know how I would get the side length which is on the hypotenuse? Okay, that's fine. Not really sure. So I think what we need to do is review the special right triangles. Okay, so I actually had a lecture where I reviewed these, but I'll point that to you later, and for now I'll just give you the information again. So we had two special right triangles. Oops. The first special right triangle was if one of the angles is 45 and the other angle is 45, then we have a 45, 45, 90 triangle. And the length of the sides obey a special rule. The rule is that if the length across from the 45-degree angle is x, then the length across from the other 45-degree angle is the same length, x, and the length of the side which is across from the 90-degree angle is x times the square root of 2. Now the other special triangle we had was if we had a 30, 60, 90 triangle, and this one had a different rule. If this one's 60 and this one's 30 and this is 90, then we said if the side length which is across from the 30-degree angle is x, then the side length which is across from the 60-degree angle will be x times the square root of 3, and then the side length which is across from the hypotenuse will be 2 times x. This is the rules that we had. So what this meant was that the relationship between these two sides is always like this. So for example, if we have a 45, 45, 90 triangle, okay, if we have a 45, 45, 90 triangle, and this side length is 3, then you tell me, what is this green side length? Also 3. And how about the hypotenuse side length? What should its side length be? Yeah, 3 times the square root of 2. Good. Let's do one more practice with this. With another 45, 45, 90 triangle. If I have a 45, 45, 90 triangle like this, and this side length is 1, then what should this side length be? No, it wouldn't be 1. Remember, there's a relationship between the side length of the hypotenuse and the side length of one of our sides. They should be different. If we're talking about the one that's across from the 90-degree angle, will be different from the one that's across from the 45-degree angle. But they obey a special relationship, right? If I take the one on the right-hand side and I multiply it by the square root of 2, then I get the one on the hypotenuse. So what should I do if I have the one on the hypotenuse in order to get the one which is on the side? Not 2x. So if I know the side length which is on the side, and I want to know the length of the hypotenuse, I just take the length which is on the side and I multiply it by the square root of 2. So if I know the side length which is on the hypotenuse and I want to go the other way, I should reverse that process. So what should I do to find this side length on the side here if I already know the length of the hypotenuse? I want to do the opposite of the process that I used to go from the side length to the hypotenuse length. That's right, divide. What should I divide? That's right, divide by the square root of 2. Do you see how these two processes are the same in yellow here? If I want to go from the side to the hypotenuse, I should multiply by the square root of 2. And then if I want to go from the hypotenuse to the side, I should do the opposite of that process. I should divide by the square root of 2. Okay. So then let's find out. See if you can take a minute and check. What do you think this number in this yellow spot should be? And I'm going to be right back while you think about that. All right. What are we thinking? Do we have an idea of what we want to put in this yellow spot here? Yeah, very good. Square root of 2 over 2. Okay, so first of all, we would do maybe, what we want to do is we want to take 1 and divide it by the square root of 2. But you're right. The good thing to do here would be to rationalize this denominator here by multiplying by the square root of 2 on top and bottom. And the top would become square root of 2, and the bottom would become square root of 2 squared, which is 2. So that's what should go on that side. Okay, so this is really what we need to remember about these special right triangles, is that if we want to go from one side to one of the other sides, we need to remember what we should do in order to move from one side to another side. So for a 45, 45, 90 triangle, if we want to move from one of the sides to the hypotenuse, we multiply by the square root of 2. And if we want to move from the hypotenuse to one of the sides, we should divide by the square root of 2. And this is how we find out what the other side lengths are without having to use like the Pythagorean theorem and that sort of stuff. Okay, these special right triangles, we have this relationship of we know what the relationship is between the sides. We know how to move from one side to another side. Okay, so do you feel a bit more confident with the 45, 45, 90 triangle? Okay, good. So what's the other side length? What should go here? Same thing, exactly. That's the special property of the 45, 45, 90 triangle, is that the lengths of the two sides should be the same. Okay. I think we're good on 45, 45, 90. Let's move on to the 30, 60, 90 triangle. Okay, so for this one, we have the following relationship between the three sides. We have that one side length is x. That's the one that's across from the 30. Okay. And the other side lengths are x times the square root of 3, and then 2 times x. So here's the deal. We know how to move from one side to another in the following way. If we want to go from this side to this side, we multiply by the square root of 3. If we want to go from this side to this side, we should divide by the square root of 3. If we want to go from this side to this side, we should multiply by 2. If we want to go from this side to this side, we should divide by 2. Then the last one is the trickiest. The last side is the trickiest to figure out what we should do. Well, if we want to go from this side to this side, we should multiply by 2 and divide by the square root of 3. And if we want to go from this side to this side, we should multiply by the square root of 3 and divide by 2. Okay, so this is our key for what we should do on a 30, 60, 90 triangle. It's a little bit harder in the 45, 45, 90 triangle because we have 3 different sides. Okay, so let me ask you a question now. Say I have a 30, 60, 90 triangle. And this side here is 3 times the square root of 3. Can you tell me what the right-hand side should be? Maybe I should bring this back. Just thinking, what is square root 3 divided by square root 3? Well, it's a good point. Square root 3 divided by square root 3 is in fact 1. So what is 3 square root 3 divided by the square root of 3? Okay, let me ask you a follow-up question. What's 3x divided by x? Yeah, 3. So what's 3 times the square root of 3 divided by square root 3? Hint, let x equals square root 3. Yeah, just 3, right? We just take the square root 3's and we cancel them. Same way that we cancel the x's before. So, what should the side length be? Thought it was similar to what I did in homework, though. I'm not sure what you mean. Thought it was similar to what I did in homework. Can you explain what you mean by that? You can also use your microphone if that's easier. I don't think so. Those two things are definitely not the same. 2 square root 3 over 2 is just the square root of 3 because we cancel the 2's. Now, if you had something else that was, if you had 2 divided by the square root of 3, then the way you would rationalize that would be by multiplying by the square root of 3 times over the square root of 3, and that would get you 2 times the square root of 3 over 3. Is this what you're talking about? Yeah, this is just a rationalizing the denominator, though. This part here in parentheses is just 1. So it's just about getting the denominator to be rational. So just like what you did with the square root of 2 over 2 part. Okay, you divided by a square root, so you wanted to fix the denominator so it wasn't rational anymore, or it wasn't irrational.
I want to make sure. Can you hear me?
Oh yeah, I can hear you.
Okay. I just want to make sure. This is what I'm using is not really a mic. I had to buy a new one.
Hang on one second. Let me put this headphones on. I don't bother my wife too much. All right. Sorry, go ahead.
I was just saying I had to buy a new mic. This is just headphones. They don't really have a mic.
Gotcha. Okay. Well, why don't we go back to our triangle here, this 30, 60, 91. So we established, right, that we got this side length with the number 3, right? We got that from taking the side length on the bottom, which was across from the 60, and dividing by the square root of 3, right?
Yep.
Now, how do I get the side length, which is across from the 90?
Multiply by 2, so would that be 6?
Yeah, we take the side length, which is across from the 30, and we multiply by 2. So that's 6. Or we take the side length, which is across from the 60, and we multiply by 2 divided by the square root of 3. Okay, those are the two ways we could get to that side.
All
right.
2 divided by the square root of 3, would that still equal the same answer?
Let me show you why. So if we take the side length, which is across from the 60, and we multiply by 2 divided by the square root of 3, anything we can cancel here?
Oh, okay, the square root of 3 can cancel out.
Yeah, and you wind up getting the same thing, right?
Yeah. Okay.
So yeah, you can go, this is just about how we can go from side lengths to side lengths on a 30, 60, 90 triangle. Okay, so my recommendation would be to put this somewhere in your notes. Okay, these two diagrams where we say, okay, we know how to go from one side to another side of a 30, 60, 90. And we know how to go from one side to another side of a 45, 45, 90. Okay? So let's return now to our original discussion, which was the following. We had a 30, 60, 90 triangle, which was inside of the unit circle. And because it's the unit circle, we know that the side length, which goes from the very center of the circle to the very outside of the circle, should have length 1. So we have a 30, 60, 90 triangle here. Okay, so I'm referring to this 30, 60, 90 triangle in blue. And we know the side length, which is across from the 90, is 1. So you tell me, what should the side length be, which is across from the 30?
Would that be 1 over 2?
That's right, 1 over 2. And what about the side length that's across from the 60?
One over 2 times the square root of 3, which would equal square root of 3 over 2, I think.
Yeah. You don't gotta think, you got it perfectly right.
I tend to second guess.
That's okay. Lots of people do that with math, myself included. Okay, so I know that this length here is square root 3 over 2. And I know that this length here, use a different color. This length here is 1/2. So can you tell me what are the coordinates of the point x comma y on this unit circle?
$60 or pi over 3, I think.
Well, I'm looking for the coordinates of this point here, which is a point in coordinate space. So for example, if I want to graph the point 3 comma 5, what I do is I go over 3 units, and then I go up 5 units. And then that's the point 3 comma 5, right? So I want to know, if I look at this triangle here, it kind of tells me how far to the right and how far up and down I should go. So if I want to get to that point, I could just walk along the bottom side of this triangle for however long it is, and then walk up the side of this triangle, which is facing up and down, for however long it is, and go to that point. So what should the coordinates of that point be?
The coordinates would square root of 3 over 2 be x, and 1 over 2 would be y.
Exactly. So this is how we used a 30, 60, 90 triangle to figure out what the point is on the unit circle, which gets pointed to by a 30-degree angle. Okay?
Okay.
And here's where sine and cosine come in. If you give me an angle, okay, I can put it inside the unit circle and it points at some point on the unit circle, right? For example, if you gave me the angle 30, like you did, then I can tell you that there's a point on the unit circle. It's the point square root 3 over 2 comma 1/2, and that's the point that the angle 30 degrees points at. Right?
Right.
And we call the x-coordinate cosine of 30 degrees. And we call the y-coordinate sine of 30 degrees.
Okay.
So cosine is just the word we use. Okay. The cosine of 30 degrees is the terminology we use to express the x-coordinate of the point on the unit circle, which the angle 30 degrees points at. And likewise, sine of 30 degrees is just the terminology which we use to describe the number, which is the y-coordinate of the point on the unit circle, which gets pointed to by the angle 30 degrees.
Okay.
Okay, so let's do a practice of like what you said. Your question was, how do I find sine of pi over 4? So I'll let you maybe guide me through how I'm going to start this problem. You still there, Jake?
Sorry, my internet is acting weird.
No worries. So do you know how to start maybe trying this problem?
I wouldn't exactly say I'm sure how to start it.
Okay. Well, first of all, let's just focus on what's inside here. What the heck is this pi over 4 thing? It's a measurement, and it expresses something geometric.
1 pi over 4 would be like 45 degrees.
Yeah, but I mean, even less complicated than that, what I was looking for is, okay, pi over 4 is an angle, right?
Yep.
It's an angle. So if I were to draw a unit circle, which by the way, drawing a unit circle is the first step of every single trig problem ever. So get in the habit. Okay. What I want to do is then draw an angle. Okay. And the angle I want to draw should be the angle pi over 4, which I can think about in two ways. I can try to convert pi over 4 radians to degrees. And I gave you that the way we would do that is by multiplying by 180 over pi. So then we would get pi over 4 times 180 divided by pi. The pi's would cancel, and we'd get 180 divided by 4, which is 45. So that's one way to think about it. Okay, pi over 4 is 45 degrees. The other way to think about it is to remember that pi over 2 is facing straight up. So pi over 4 is like pi over 2 divided by 2, so it should be half of a right angle. Okay?
Okay.
So here's my angle theta. And I know that it's 45 degrees, or pi over 2, 4, whatever, however you want to say it. Now, can you tell me, if I write sine of pi over 4, what does this represent in terms of our picture? Sine was a special name that we had for something on the unit circle somehow.
Let
Let me go back up to what I drew up here. When we drew this angle here, we drew the angle 30 in here, and we said that the angle 30 is going to point at a certain point on the unit circle. And cosine and sine were our way of describing what the coordinates of that point were.
Oh, X and Y?
The x and y, that's right. So cosine is the x, and then sine is the y. So on my picture down here, maybe I could fill in a little bit more. I could put a point here, right? And this point has coordinates. What are the coordinates of this point?
X and Y?
X and y. And how do I say that using sine and cosine?
Cosine, sine.
Yeah, cosine of, and I'm going to put, since theta is 45, I'm going to put 45, or pi over 4 if you want. So, I have a point on the unit circle. I know that its coordinates have these special names of sine and cosine. And what I really want to know in the end is, what is this number, sine of pi over 4? Right?
Didn't that equal like the square root of 2 over?
I mean, yes, but I don't want you to jump to conclusions too fast because, I mean, you're right, but that's not a way that you're going to be able to remember how to do the process on like an exam. So let's do the process, which is the following. You want to know what is sine of pi over 4, which is to say, really, what is the y-coordinate of this point on the unit circle, which gets pointed to by a 45-degree angle? Okay. So how can I find out what the height of that point is?
When you multiply y times it, I think, or pi.
Well, here's a question for you. What did we just talk about up here? Remember all this triangle stuff we did?
Yeah.
With 30, 60, 90 triangles and 45, 45, 90 triangles. Is there a way we can incorporate that into our picture here?
Oh, 45, 45 angle.
Yeah, but so far I don't have a triangle yet.
Oh.
So can I make a triangle?
No, not yet.
Well, I have two sides of a triangle. Could I make it a triangle somehow? Anything extra that I could draw in to complete this picture into a triangle?
90-degree angle?
Yeah. Or in other words, I mean, if I have two sides of a triangle, these two yellow sides, the way I make it into a triangle is by drawing the last side, right?
Yep.
Okay, so this is the process we do. We always take our point and we draw a vertical line which goes from our point to the x-axis. That's this line here. And then this angle here, which gets formed on the x-axis, is a 90-degree angle. So what's the other angle?
45?
Good. Now, I have a 45, 45, 90 triangle. If I knew one of the side lengths, then I'd be able to figure out the other ones, right?
Yep.
So are there any side lengths of this triangle that I already know, like one of these three side lengths?
No. I don't think.
There is one that we know. So my argument is, you actually know what the length of this one is, the yellow one that's still highlighted.
Yellow. Pi.
Follow-up question. What is the length from the center of this circle to the outside of this circle?
Pi 2?
No.
Oh.
This is the
Oh,
radius. The radius of this circle is
0 over, 0, 1.
we're going in the right direction. What is the name of this circle that we're on?
I think that the center, or the, I can't find the right word for it.
So this is the unit circle, right?
Yeah.
And what's the special thing about the unit circle? What does the word unit make you think of? What number does the word unit make you think of?
0?
Not 0.
Or 1?
1. The special fact of the unit circle is that no matter where I put this pink line here, the distance from the center of the circle to the outside of the circle is 1. Okay, that's why we call it the unit circle. 1 means unit. Okay. So, because I know that this triangle is inside of the unit circle, and one of the sides of my triangle goes from the center of the circle all the way to the outside of the circle, I know how long one of the sides of the triangle is because I know how long it takes for me to go from the center of the circle to the outside of the circle. So what is this length here that should be in this yellow circle?
1.
Yeah, 1. Okay. So I have a 45, 45, 90 triangle, and I know the length of one of the sides is 1. So what should the length of the other sides be? How do I get the length of the other sides if I know what the length of the hypotenuse is?
For the right side, it's 1, would that be divided by square root of 2?
Exactly, we're going to divide by the square root of 2. So this side length should be 1 divided by the square root of 2. How can I rationalize that?
Square root of 2 over square root of 2, which then equals square root of 2 over 2.
Very good. So this side length going up and down is square root of 2 over 2. And how about the other side length going left and right?
Yes. Square root of 2 times 3? No.
Well, you have a 45, 45, 90 triangle. There was a relationship that we had between the two side lengths of a 45, 45, 90 triangle. And it's similar to the relationship between the angles 45 and 45. Since the angles 45 and 45 are the same, the side lengths, which are across, will also be the same.
I keep forgetting.
So this should also be square root of 2 over 2. Okay. So, what are the coordinates x comma y of this point?
They're both the same, square root of 2 over 2.
So what is sine of pi over 4?
Sine of pi over 4. Wouldn't it be the square root of 2 over 2?
Exactly. It's going to be this y coordinate, right? This is what we were after the whole time, was the y coordinate of this point. And used the 45, 45, 90 triangle to figure out what the lengths of the sides were. So our answer at the end is square root 2 over 2. Okay?
Okay, I think I understand now.
Okay, so let me just remind you, the way that this final statement reads is the following. The left-hand side says sine of pi over 4. What it says really is the y coordinate of the point on the unit circle, which is pointed to by the angle theta equals pi over 4. And the equal sign means is. And then the right-hand side is the height of that point. Make sense?
Yeah, it does.
So then how could I fix this if instead the question was, what is cosine of pi over 4?
When you use the x?
Yeah, then it's going to be the x coordinate of the point on the unit circle, which is pointed to by the angle pi over 4. And what should cosine of pi over 4 be?
Square root of 2 over 2.
Yeah, also square root of 2 over 2. Because this time we're going to take the x coordinate of this point. So in this case, this square root of 2 over 2, which we put here, it came from the x coordinate of the point. Okay?
Okay.
All right, last question. What is tangent of pi over 4?
I'm not really good with the other ones like CSC or tan.
Okay. So here's what we say about tangent. if I have an angle theta, and theta corresponds to the point x comma y on the unit circle, you know how we said the x-coordinate is the cosine and the y-coordinate is the sine?
Yeah.
Tangent theta is the y divided by the x.
Oh.
Okay. So how would I get that for pi over 4? If I want to take that y-coordinate and divide it by the x-coordinate, what should I do?
Wouldn't it be like the same process of trying to find a unit circle, but in the end you would divide both y and x, which in this case would be square root 2 over 2 divided by square root 2 over 2.
What do I get?
Or when they equal 1.
That's right. All right, so we get 1.
What about the other ones? Because I slightly remember that there was one where you like divide x, y. There was one that was undefined, and the other one was the last one. Sure.
Here's how we define the other trigonometric functions. We have tan theta is going to be the y-coordinate divided by the x-coordinate. Cosecant theta is going to be 1 divided by the y-coordinate. Secant theta is going to be 1 divided by the x-coordinate. And cotangent theta is going to be the x-coordinate divided by the y-coordinate. So this is the definition we have for the other ones, okay?
Okay.
And I put CCS here. I meant to put CSC. Sorry. All right, so that's how we find all these other ones. So the way you would find these is just by taking these x and y coordinates and plugging them in. All right.
Okay.
Okay, so that's how we do this trigonometry stuff. Okay, so here's the deal. I want you to do something for me. Actually, I want you to do something for yourself. Sometime between now and Wednesday. I want you to go on the YouTube channel. And I want you to watch 2 videos. Let's see if I can find them. Actually, I want you to watch 3 videos.
Would that be lecture 28?
Yeah, lecture 28 is the one that you should really watch. If you need a little bit more work with angles and how to convert between angles, I suggest you watch lecture 27 as well. It looks like I put two different lectures as lecture 28. But you should watch both of those videos, okay?
Okay.
So those you can watch before our lecture on Wednesday. And then, I think you're a little bit behind on this trigonometry stuff. So, if you want to get caught up, I'd probably recommend that you try and hang out a little bit during office hours on Wednesday as well, okay?
Okay, I will.
All right, cool. So why don't you try watching those lectures, make sure you kind of get an idea of that, practice finding those trigonometric functions for different angles of theta, and then we'll meet up on Wednesday and talk a little bit more about trig. I'll have a lecture and then office hours afterwards.
Okay.
All right.
Yeah, thanks for the help.
Yeah, no problem. It's my pleasure. Okay, so if you need more help, just let me know. Okay, if office hours isn't enough, then you can always email me as well. Or I can connect you with the people in the math tutoring center. So like other graduate students like me are just kind of like in there all day, every day, Monday through Friday. And you can just go and talk to them like you talked to me today. For, you know, as long as you want, or at times that work better for you if you want.
Okay. Thanks for the help. And you have a nice day.
Yeah, you too. See ya.